Hello and welcome to this episode of Math with Martinez. In today's video, we are going to be introducing sequences and furthermore looking at writing the equation or the formula, I should say, in either recursive form or explicit form for our sequences. Let's go ahead and begin by first defining what exactly is a sequence? Well, a sequence is simply a set of numbers. It is a set of numbers with a particular order or pattern. Let's underline that part right there. It has a particular order or pattern. That's really important to be aware of. Your sequence is not just random, but there is this structure, this order, this pattern to it. And each number in your sequence is called a term. This is a important word that we're going to use a whole lot. So you may want to take a moment to just be aware of that and maybe highlight that as a keyword. Now, there are different types of sequences. The first type, right, this number 1 here, is going to be a finite sequence. A finite sequence is a sequence with a finite number of terms. Let's highlight that word, finite. What does that mean? It means that you can count the number of terms. You can count the number of terms in your sequence. For example, the sequence 1, 2, 3, 4, 5 is a finite sequence because we can count, there are only 5 terms. We can count up the number of terms. All right, so let's put that in a little bubble so that we remember that is what makes it finite. Now contrast that with an infinite sequence. An infinite sequence is a sequence with an infinite, let's highlight that, an infinite number of terms, meaning that we cannot count all of the terms. Maybe this would be a good example because what we're looking at is there's no end, that there is no end to our sequence. I could not find the end or count the number of terms there. So this set right here is an example of an infinite sequence. All right, now, how do we as mathematicians notate terms? The first term in a sequence is always denoted as A1, And each subsequent term, or each term after, is denoted as A n plus 1. Where A n is the number of its position in our sequence. So take, for example, this first little sequence, 2, 5, 8, 11, 14. And what we want to do is identify our terms. What would A1 be? Well, A1, the way that is written, represents the first term in our sequence. The very first term is 2. This is the second term, third, fourth, and fifth term. So now I know that the fifth term, A sub 5, is 14. Now listed is not the 8th term, A8, but we can go ahead and find it because what are we doing each time here? What are we doing between each of these terms? What is the pattern that exists? Well, each time we are adding 3. So our next term would be 17. Let me write this in a different color. Our next term would be 17, and then 20, and then 23, and then 26, 29. After that, we would have 32, and after that, 35, 38, 41, and this keeps on going, but let me number what I've got so far. This is 6, 7, 8, 9, 10, 11, 12, 13, and 14. So, ladies and gentlemen, what is A8? What is A8, or the 8th term in our sequence? That is going to be 23. And what about A14? The 14th term in our sequence, what is that going to be? That's going to be 41. So since each term's value, like we just saw above, is paired with exactly one number, a sequence is actually a type of function with the following properties. The domain of the set is the term numbers. Those are the term numbers, or their position. I like to say their position in the sequence. And so our domain in this example would be all the n's, their position, their number of that term. And the range of the set is going to be the term's values, meaning what is the value at that position. An infinite set, the domain, is the set of all natural numbers, meaning those counting numbers beginning at 1. So we go through all of that, and now we talk about the formulas, the way that we can write a formula to define our function that is our sequence. A recursive style of writing our formula is just a rule where one or more previous terms are used to generate the next term. So you're going to be writing it with respect to the previous terms. So take, for example, a very familiar sequence called the Fibonacci sequence. It looks like this: 0, 1, 1, 2, 3, 5, 8, 11, oops, sorry, not 11, 13, and then 21, and then 34, and it is infinite, meaning it goes on forever. Those are the values of our terms in this sequence. So if our sequence begins where A1 is 0 and A2 is 1, meaning those are the first two, then how would we write the formula to generate the subsequent terms? Well, it would be to say that AN is to take its previous term, which is AN minus 1, where that just means N minus 1 is what came before N. And what do I do with that? What do I do with that? Well, look at what we've got here. In our Fibonacci sequence, if you take the first two terms, 0 and 1, the third term is 1. Then look at 2. 2 is the result of taking 1 and adding them together. 3 is the result of taking 1 and 2 and adding it together. 5 is the result of taking the 2 previous and adding it together. 8 is the result of taking the 2 previous and adding it together. And that is how the pattern continues. It's always just take the 2 previous, add them up, and that's how you get the next term. So what we're going to want to do is take the two previous, which is to say an minus 1 and n minus 2, and add them together. That is an example of a recursive formula. So given that recursive formula, let's give the terms in this sequence here. We know that A1, for example number 1, is 25. So we know the first term is going to be 25. And then what does it say we want to do with that? We want to take an minus 1, an minus 1. That means take the previous term, the term before that one, and subtract 7 from it. Subtract 7 from it. So what does that look like? It means that we're going to go ahead and take that first term and subtract 7 from it to get our next term. So 25 minus the 7, that's going to be 18. And then take that term and subtract 7 from it, 11. Take that and subtract 7 from it, well, that's going to be 4. And take that term and subtract 7 from it, negative 3. 1, 2, 3, 4. That's all 5 of them. That's an example of using your recursive formula. Let me highlight that recursive formula here for you. We used this recursive formula to go ahead and find those terms' values. Now I want to do just a couple more here with you all. Let's look at number 3. Number 3, our recursive formula is right here. It says that the nth position is going to be 1/2 the previous plus the previous term. You could even label this. What does the n minus 1 mean? The term before. That's what it means. So we're going to take half of the term before plus the term before. So we already know, you can kind of create a little table right here if you wanted to. Maybe we'll do it horizontally. Right? And nope, you're right. It would work better to do it vertically. So let's go ahead and begin. So we're going to do n and an. We know that the first term is 40, right? We know our first term is 40. That was given to us. Now our second term is going to be 1/2 of our previous term, which was 40, then plus 40. So what is half of 40? That's 20 plus 40. That gives us a total of 60. Now let's move on to our third term. It's half of the previous term, which was 60, plus 60. That's 30 plus 60, which is 90. Can you guys figure out what the next term, our fourth term in our sequence, would be? It's half of 90 plus 90, which is 45 plus 90. That's 135. And we've got one more. What is that fifth and final term going to be? All right. We should have half of 135 plus 135. And with a little bit of help from your calculator, you'll find that to be 202.5. Now, to ask you to do something a little bit different here, we have our sequence, and we want to write the rule for it. Let's go ahead and write the rule for it. Well, we already know our first term, A1, is 9. And now we want to write our formula in terms of n. So what do we do what do we do? Let's compare these terms with one another. What did I do to 13, or what did I do to 9 to give me 13? What did I do to 9 to give me 13? What was the step between here? It looks like to go from one to the next, I would add 4. Is that consistent? Adding 4. Yep, consistently adding 4. Adding 4 to go from each. So what does that mean? I take my previous term, which is an minus 1, and add 4 to it. I simply add 4 to it. And I do need to specify that that means that our n has to begin at 2. Because if you plug in, just to clarify why is that? Because A2 is A2 minus 1, which is what? What is 2 minus 1? That's actually just a 1 plus 4. You see how that means we're going to begin at our second term. Given our first term, now let's move on to the nth term, which be our second term. And then it would work from there on out. Just to clarify there. Now, I want to contrast these recursives with explicit formulas. An explicit formula is going to be a rule where the nth term is defined as a function of n. So you don't look back, you just base it on right there at that position, at that moment. So looking here at number 7, what does this mean? This means that, well, if I want to know the value there, all I need to do is plug in the nth position. That looks like saying, okay, let me make this nice and neat here for you. And we'll put our answers up here. So we'll begin at n being 1. So what do we do to find that first value? We would just take our function and plug in that value for n, which is going to give us 6. So we know our first value is 6. Our second value is going to be 5 times 2 plus the 1. That's going to be 11. Our third value is going to be 5. Now plug in that value, add 1. And what is it at 3? That's going to be 15. 16. Our fourth value is going to be, yep, you guessed it, 21. And then our final value, barely have room. Our final value, let me do this and then we will have enough room. I bet you wish you could do that on your paper, don't you? Just scooch things around like that. It's so nice. Okay, so that's going to be, and giving us our final value of 26. That would be the first 5 terms in that sequence. So you can see here that sometimes it's nice to have some scratch paper to think it through, or maybe you just do this mentally. Why don't you guys try number 9? Can you try number 9? Plugging in, kind of like I did here for those positions, the nth value, and simplifying those fractions. So we would begin with a 1 minus 1, that's going to be 0. 0 divided by any number is 0. Then what we're going to have on top, when we plug in a 2, it would be a 2 minus 1 over 2 plus 2. That's going to be a 1/4. Then when you plug in your 3, that's going to be a 2 over 5. Your fourth position, that's going to be a 3 over 6, which simplifies to 1/2. And last but not least, our fifth position, that's going to be a 4 over 7, which cannot be simplified anymore. Now let me bounce down here to example number 13. This is to write a rule based on its position, an explicit rule. An explicit rule. So that means to write it as AN equals. Now how do I get that first position? How do I get that first position? What seems to be happening here each time? What happens here each time? Don't look back, but based on its position, how do you get that number? 1, 4, 9, 16, 25. What is happening to your n value? What is happening to your n value each time to get those different outputs? It's really just your position squared, beginning at that value where your n is 1. Now it also wants us to find A25. Well, A25 would just be 25 squared, which is 625. So ladies and gentlemen, let's be just about done here with this last example 15. For this sequence now, let's write both an explicit and a recursive rule. So now that we've seen both, for this given sequence, let's figure out our patterns. Let's begin with an explicit. This is to say AN, in terms of the position, how do you get that output? You would have to say beginning at 1, at an input of, when my input is 1, when my input is 2, 3, 4, and 5, how do I get those outputs? Okay, well, from 1 to 4, that looks like adding 3. But if I add 3 to go from 2 to 7, that doesn't work. That doesn't work. Okay, so let's see. What could we do? What if I take this? What if I take 3 times it and then just add 1? Does that work each time? 3 times 2, that's 6, add 1. 3 times 3, that's 9, add 1, and that's 10. Oh, good. 3 times 4 is 12, add 1. Yeah, we did it. Okay, now recursive is based on the previous. What do we do each time here? What's happening each time there as we look from one to the next, to the next, to the next? Ah, yes, you are right. I'm sure you see it, right? You're just adding 3 each time. These are nice. You just take that previous term, add 3 to it. This is what we're more familiar with doing intuitively. And we would need to say that n must be greater than or equal to 2. Because we can't go into the negative regions for our terms. We've got to begin with our first value. We've got to know that A1 is equal to 4. So there you have it, ladies and gentlemen. Explicit formulas, recursive formulas for our sequences, whether they are finite or infinite. If you had any questions from this video, please take a moment to write those down, to share those. What didn't make perfect sense? What would you like more clarification on? Which examples in particular would you like me to really focus on? And I will get back to your questions, comments, and concerns just as soon as I can. And until next time, stay fired up, you guys.